When we dance with a partner, receive a package from a delivery person, or help a friend move a piece of furniture, we coordinate action with another person. These cooperative tasks are often achieved without any verbal communication, relying solely on visual and haptic cues. In this work, we ask how partners might use these nonverbal cues to delegate specialized roles. We implement a genetic algorithm to create a population of dyads capable of performing a simulated cooperative task. We then explore the genomes of the most successful dyads to see what makes for good cooperation. In our model task, partners sit across from each other and push on an object, an egg. Their goal is to push the egg along a prescribed path without crushing or dropping the egg. Because the normal force on the egg is equal to the minimum of the two agents' forces, at any given time, only one agent affects whether the egg stays intact. Agents are imbued with two separate force controllers, one to track the reference trajectory and one to stabilize the normal force, corresponding to roles T and S, respectively. For each agent in the dyad, we evolve two switching policies based on the haptic and visual cues that determine when that agent changes their role from S to T and vice versa. After evolving thousands of successful dyads, we observed a few common traits in the population. The best performing dyads exhibit remarkable temporal coordination. Agents generally assume opposite roles and swap roles at nearly the same time. We define anti-synchrony as the fraction of time that agents assume opposite roles. If we look at the distribution comparing performance and anti-synchrony, we see that at the leading edge, better performance requires greater anti-synchrony. But what makes dyads coordinate well? We inspect their genomes in search of a pattern. Each dyad comprises two agents, and each agent has two switching policies. We compare the policies of the two agents by calculating a symmetry coefficient for the policy vectors. Symmetric policies make the same decisions given the same inputs. Anti-symmetric policies make the same decision given opposite inputs, like partners sitting opposite each other would perceive. If we compare policies from a random sampling of the population, we get these distributions. But if we look at only the top decile of most anti-synchronous dyads, a pattern emerges. Complementary policies between agents are more anti-symmetric. Our genetic algorithm has evolved dyads that use this asymmetry to arrive at temporal coordination. Good partners complement each other.